In this video, I am exploring the training process of machine learning, focusing on the introduction of validation. So far, I have viewed a neural network as a mathematical function with input and output vectors of real numbers. Training involves adjusting parameters to improve the model's performance. To simplify for those with math anxiety, we can think of the model as a gray box with parameters controlling how the input is mapped into an output. We have concentrated on supervised learning, where each dataset sample includes an input and an expected output. The model parameters initially have random values. Training starts by inputting a batch of inputs into the model, which generates an output. The output is compared to the target to calculate an error, known as loss or cost. This error is then used to update the model parameters to minimize the error. The dataset is divided into three subsets: training, validation, and testing. The validation subset evaluates the model's performance during training, while the testing subset is used after training. These subsets are not involved in the learning process. A well-performing model can be deployed for real-world applications. Let's review the TensorFlow code. It is similar to the code we previously used, with some minor modifications. I included the input layer as the first layer to address a warning I encountered. The validation split is set to 0.2, allocating 20% of the data for validation. Accuracy and loss metrics are computed using the training data, while validation accuracy and loss are calculated using the validation data. The test subset is utilized for testing the model. I conducted 2 independent runs, both yielding similar results. Starting from epoch 10, the validation loss begins to increase, indicating a decline in the model's performance on the validation set. This suggests that the model is becoming less effective at generalizing to new data. Let's explore how PyTorch handles validation. We will make modifications to the previous code to highlight key points. The model we define outputs the final linear summation, which aligns with the cross-entropy loss. The training code undergoes significant changes, with forward and backward passes, training losses computed as shown in previous videos, and we will now delve into calculating accuracy. In digital circuits and machine learning, one-hot encoding is a binary representation where only one bit is high and all others are low. In neural networks, the output after training may not always be ideal. The unit with the highest value is considered hot, while the others are considered cold. To understand how we find the hot unit, let's look at the 10 output values represented by empty squares. Keep in mind that training handles data in batches, so the output data is two-dimensional. We need to find the maximum value along each row, which is why the dimension parameter is set to 1. The value returned by the max function consists of 2 components, the maximum values along each row and the indices of the maximum values. Pause the video to check the code. These indices are taken as the predicted target values and then compared with the true labels. The number of matches between predictions and true labels is added to a variable that stores the running sum of correctness. The batch number is only used for showing the training progress. After one epoch of training, the average loss is stored, as well as the average accuracy. Let's explore how validation works in PyTorch. The code is based on the skeleton shown here. First, we switch to evaluation mode and turn off gradient calculation. Then, we calculate the outputs and loss values using the validation data. We want to monitor how the losses change during training, as well as the accuracies. We need the total number of samples to calculate the mean value. The final step is to test the model after the training is completed. After training, I realized that I didn't split the MNIST dataset into 3 parts as I did in the TensorFlow code. I was unsure why it's not recommended to use the same subset for both validation and testing, so I asked ChatGPT about it. Here is the answer. If the validation set is repeatedly used for tuning the model, it's as if the model is exposed to the validation data multiple times, increasing the risk of overfitting to that specific data. Feel free to pause the video if you want to read more information from this ChatGPT answer. We just need to make slight modifications to the code to create 3 subsets. There are various ways to split data, and here we will use the train-test-split function from scikit-learn. Before delving into the code, let's look at a simple example of the train-test-split function. The variables inputs and labels are arrays, and we will split the data into 2 parts using this function. We make 2 function calls. With the first call returning the training set and the test set. The test set is not displayed here. The second call of the train-test-split function returns the indices of the input samples. In both cases, the labels are not distributed in proportion to the original dataset. By passing the stratify parameter to the function, the resulting labels are distributed proportionally to the original dataset. In our PyTorch code, the function split_train_test returns the training and validation indices, which are then used to create the training and validation subsets. We now have 3 datasets, each of which is used to build a corresponding data loader.